You've just watched my beautiful little daughter run 10 meters in 12 seconds. I want you to, on this graph, the first part in the notes, in the section 3B notes, I want you to plot her initial position, her final position, and then calculate her velocity. Pause the video until you do so, and then resume once you have done that. Okay. Hopefully you got that taken care of, and what you should see is her initial position would be right here at 0, 0. That's her there. And she ended up at 10 meters 12 seconds later. So that's her there. Now basically she was going at a constant rate the entire time, and so her velocity would be the change in position over the change in time. So her change in meters divided by her change in seconds. So she changed by going. She ended at 12. She ended at 10 seconds, but started at 0 seconds. She ended at 12 meters, but started at 0 meters. So that's a velocity of 10 meters in 12 seconds. That reduces to 5/6 meters per second, which is about 0.83 meters per second. So that was her velocity. Do you recognize, though, that the way I calculated this velocity is exactly the way I would have calculated the slope of this line? Slope is calculated by finding the change in y, usually doing y2 minus y1, over the change in x. So I would have, again, 10 minus 0 over 12 minus 0. And so I get that 10/6 again. 10/12, which is 5/6. So do you recognize that the velocity is really equal to the slope of my graph here? Do you see that connection? Hopefully that makes sense to you. Now, I decided to run the same course as my daughter, and as you can see I started at 0 seconds just like she did. I finished at 5 seconds but didn't quite make it. Well, I finished at 5 seconds. I was at 5 meters when I did. So now I want you to go back into the notes to the next graph, which says Big Desserich, position versus time, and I've actually already got my initial position and my final position. I want you to go ahead and calculate my velocity. Press pause until you do so, and then resume. Okay, so just like for my daughter, my velocity would be my final position, which would have been 5 meters, minus my initial position, which was 0, divided by my final time, which was 5 seconds, minus my initial time, which was 0. So I ended up going 5 meters in 5 seconds, a velocity of 1 meter per second. Again, velocity and slope are the same thing. The slope of this line is 1. So I was going 1 meter per second. It's not very much faster than my daughter. Or was it? Watch this next video and see what actually happened. So really my path went something more like this. Instead of going straight from initial position to final position, I actually ended up going all the way to 10 meters and then coming back. So calculating the slope of this line here really only shows you my average velocity. And it's really not that accurate. I'm not actually going 1 meter per second. Here might be a better calculation of how to figure out my slope. Doing the slope of my velocity. Doing the slope of this line. So going from a final position of 10 meters minus my initial position of 0 meters divided by a final time of about 2.5 seconds minus my initial time of 0 seconds, and we find out that the slope of this line, which is my velocity between my initial position and that end of it 10 meters later, was actually 10 over 2.5, which is 4. So I actually was traveling 4 meters per second. A lot faster than the original 1 meter per second, and a lot faster than my daughter. So you can see this actually gave me a much more accurate picture of my velocity by finding the slope of this line, which was the x value was a lot smaller than the x value of the original one, and that ended up giving me a more accurate picture. Both of these lines are considered secant lines because they touch the curve twice. A secant line, if you remember circles back from 10th grade or maybe even 9th grade, secant lines touch curves in two different places, and so these are both secant lines. But the secant line that had x coordinates more closely together is the more accurate picture of my actual velocity. So we're going to use that idea that a secant line, the slope of a secant line, can give us the velocity on a curve to actually calculate the velocity of a different function here, not one where we don't have the actual the visual or the numbers in front of us. So this function gives us our position f of x based on our time x, and so to find the velocity between times 0 and 1, we need to find the slope of this secant line. So the line in between this point and this point. Well, to find a slope, again, we need to do y2 minus y1 over x2 minus x1. And so some of this is very easy. The x's should be very easy. x2 is 1 second. x1 is 0. y2 is going to be the most complicated here. But since this red function gives us our position based on time, I can just go ahead and plug this x, into this function up here and get the y for this position, because this will be x2, y2 is our point up there. And so if I want to find that y2, I just need to plug this x sub 2 into our function. And so I go ahead and do that. So I want to find f of 1, which would equal negative 9.8 times 1 squared plus 18 times 1 plus 8. And so that would equal negative 9.8 plus 18 plus 8, and that equals 16.2. So 16.2 is my y sub 2 here. So we just figured out that 16.2 is the y coordinate here. And again, our x coordinate was 1. We need to do the same thing to find the y coordinate here so that we can plug it in, because we need to do y2 minus y1. Well, here's our point x1, y1, and x1 we know is 0. So to find y1, we're just going to take that x1 and plug it into the function. So to find f of 0, we're going to plug it into the function, and so it's going to be negative 9.8 times 0 squared plus 18 times 0 plus 8. Well, this zeroes out, this zeroes out. We're left with the idea that when we input a 0, we get out an 8. So the coordinates of this point are 0, 8. So then y1 here is 8, which means our average velocity between this point and this point would be 8.2 over 1, or 8.2 meters per second. Not meters squared, meters per second. Okay, so now we're ready for the last step, where we're going to take all this very specific information and get very general with it. So here we just have a general old function. And let's say, and so here's it's pictured. When I input an x, it outputs a y. So let's say when I input this x, it's going to output this y. Or another way to put it is it's going to output this f of x. So when I input the x into my function, it will output a y, and that will be this coordinate right here. So sometimes we like to write this coordinate as x1, y1. We can actually write it as x as the input. The output will be f of x, whatever I get out when I plug it into whatever function represents this graph. Again, we're going very general here. Now, let's say I want to find the slope of the secant line between these 2 points. So this is my first point here. My second point is just an extra x distance away. And for that, we're going to just call it h. We scooted over on the x-axis, a distance of h. So now, what are the coordinates of this new point? Well, the x-coordinate is just going to be the initial x-coordinate plus that value h. So that's going to be the x-coordinates of this point. The output, or the y, will be, I will take that whole x plus h and plug it into the function. I'll plug it into whatever the function is. I'll plug in that x plus h, just like we did before. We plugged in a 1 there because it was 0 plus 1. We're going to plug in whatever x is plus this distance h and get out a y, and that will be the y coordinate of this point. I know this is very general, but we're going to try to see if we can understand this here. So to calculate this slope, the slope of this secant line, we would have to do y2 minus y1. But if you think about this, this is our y2 and this is our y1. So the slope would be f of x plus h, whatever that is, whatever that output turns out to be, minus y1, which is just f of x. We would divide all of that by x2 minus x1. So but this is like our x2 now, and this is like our x1. So we would have in the denominator here x plus h minus the initial x coordinate, which is just x. Now see how the x here and the x there, they would cancel out. So really the overall slope of our secant line of any function will always be f of x plus h minus f of x all over, again those canceled, all over h. That is going to be the slope of the secant line of any function you can ever find. That turns out to have a name, and that name is the difference quotient, which is what the next part of class is going to be about. So the difference quotient, as we wrote it, is f of x plus h minus f of x all over h. Now h is just any other old variable that we find that it's a distance further away from the initial x. And what we want to do is we want to make sure we plug in x plus h to the function for this first part here. It gets pretty challenging as you manipulate it, but fortunately I've got a couple of YouTube videos for you here where you watch another friend of mine go through and show you how to do examples on the difference quotient. So this video ends here. You're going to go ahead and click on each of these and watch this teacher do some difference quotient problems, and then after that you're going to go through these examples on your own. Remember that the answers to these problems are going to be in the completed version of the notes, which are in the next tab. Good luck and enjoy.